Dear colleagues, today there is an important special event, the joint seminar of Stеклова Mathematical Institute at the workshop on proof theory. And we are very happy to introduce Professor Albert Visser from Utrecht University. He will speak about one of the most famous results in mathematics and beyond. The title is, What is the Gödel's second incompleteness theorem? Indeed, what it is.
Well, I'll do my best.
Now Professor Beklemishov will say a few words.
Thank you very much. So, since not only participants of our conference are here who all know Albert Visser very well, but also people from Steklova Institute, I would like to say a few words about Albert Visser. He is the most, I would say, the best living specialist on the topic of Gödelian incompleteness. So everything which is related to the phenomenon discovered by Gödel is really still a topic of current research, and sometimes very deep theorems appear in this direction. And Albert Visser is one who contributed probably the most towards this topic. Apart from that, he is well known for his work on various things in mathematical logic, such as the study of paradoxes, the study of applications of logic in linguistics, dynamic semantics, and of course, Visser is a representative of the famous Dutch school of intuitionistic mathematics founded by Brouwer. And of course, everything related to intuitionism, intuitionistic arithmetic, and theories, constructive theories are influenced by his work very much. So I can also say that I know Albert Visser more than half of my life, so more than 25 years. And I'm very happy that now Albert will speak here on our favorite topic.
Okay, I'm very happy to be invited here, and of course honored to be in both the workshop and in the Steklov seminar. So yeah, so my talk will be really on the question what Gödel's second incompleteness theorem is, right? So I'm not going to explain proofs. I'm not going to try to formulate the most general version for you, but I'm really focusing on what does the theorem say. But before starting, let me say that it's also a very joyous occasion because it's the occasion of Lev's 50th birthday. Here we see him. Well, I thought of saying jokingly that he was standing in front of his ancestors, but that's definitely not really true. But there's a different joyous occasion today. Dick de Jong became 78, so it's in fact a kind of double joyous occasion. Okay, so now over about the second incompleteness theorem. Yeah, so I think it's probably fair to say that most mathematicians know some formulation of the theorem, but when you would press them, then of course very quickly you get to a point where they cannot say more. And so I think the kind of formulation that most people know is simply that sufficiently strong theory cannot prove its own consistency. But yeah, such a formulation evokes as many questions as it answers. So what is a theory here? What do you mean sufficiently strong? And so what is a consistency statement? And I'll try to answer all these questions at least to some degree in this talk. Now G2 has an additional problem, namely there is simply no statement of it that really reflects our intuitive understanding of the theorem. So yeah, regrettably I didn't have time to quiz some mathematicians, so maybe it's also true that for the really great theorems in mathematics, the real specialists also feel that no formulation really covers what the theorem says. But then I want to say that for the second incompleteness theorem, this situation is, in some sense, particularly urgent. And in fact, nobody really knows how to improve the usual statement in such a way that it really covers what we intuitively understand. Okay. I'm first going through the different ingredients that we need to understand the theorem step by step, right? So the first notion that we need is, what is a theory? And so, so logic produced a rather stable notion of what a theory is. A theory is a first order theory, and we are assuming that the axioms of the theory can be given in some effective way, right? So this is then a recursively enumerable theory of finite signature. I'm also assuming that the language of the theory is finite. So first order logic is really the logic of the quantifiers for all and exists. Okay, so now, as I said, I'm not aiming for the super generality. Of course, there are versions of the theorem that work for theories that are not recursively enumerable. And in fact, Lev is studying such series. There are versions for series not in finite signature, for series that are not first order, but we will refrain here from speaking about them. So the other talk I'm giving tomorrow will precisely be about such extensions of the theorem. Okay, so now what I want this to do is to state this theorem for, in some sense, for any theory, right? So I want this to state the theorem for some formulation of Euclidean geometry. I want to state it for set theory. I want to state it for arithmetic. So, and take your favorite theory, and I want to state it for that theory. But now the point is, of course, that in the second incompleteness theorem, we speak about consistency, and that is formulated in some specific language. So you need a machinery to make what you say language independent, and the notion that one uses for that is the notion of interpretation. So what is an interpretation of one theory in another? Well, roughly it's a translation of one theory in another. And what does such a translation look like? Well, take a predicate symbol of the translated theory, and that's translated to a formula of the translating theory. So that's basically it. And then this whole thing commutes with the logical connectives. So there are all kinds of refinements. So we have domain relativization, right? So the quantifier for all x is relativized to some specified domain. You have more dimensionality, etc. Right? So the example that you all know is the interpretation of hyperbolic plane geometry in Euclidean plane geometry, right? So you define point in the interpreted theory as point inside, if we take the Poincaré model, inside of a circle. So a line of the interpreted theory becomes a circular segment of the interpreting theory, etc. So that's basically it. So I think everybody has seen some examples of an interpretation. So so some notation. It's very pleasant to abbreviate U interprets V, and so that's I write it like this with this triangle. So the triangle suggests an ordering relation, right? It means that here you can read that U is stronger in some sense than V. And the induced equivalence relation here is, I write with 3 lines. This is a little bit different from the big Clemyshev tradition, where this means extensional equality of theories. Okay, now we need one further argument, and because we want to state that there is an important ingredient, and that's I call the basic theory, and I will dub it B. And so we want some kind of weak arithmetic that will serve to formulate the theory. And so there is a kind of amazing discovery over a number of years, is that in some sense this theory is unique modulo mutual interpretability, right? So there are all kinds of different versions, but you can translate all these versions into each other. And these series are also interpretable with basic series of strings, of trees, of sets, etc. So there is some informally rigorous argument you can make that this is the right thing. But it can have different appearances because it's only unique modulo mutual interpretability. And so, so there are several choices. One theory is called PA minus, and the other theory is a somewhat stronger theory, S12. So I will briefly explain what PA minus is, because that's for mathematicians a theory that is most understandable. So PA minus is a very strange theory, right? So there is a kind of divide between logic and mathematics. So the mathematicians want to look at series that are as tame as possible. So they want them to have decidable extensions, etc. And so there's the whole business of rings and groups, etc. Is always aimed at getting simple structures. And now the interesting thing of PA minus is that PA minus poses, you could be fooled in thinking that's really a true mathematical theory, but it's in fact, it's a logical theory. So what is this theory? It's the theory of discretely ordered commutative semi-rings with a least element. So here I have, I'm not going to run through this list, but if you look at this list of axioms, you see that it's very simple. So this list was given by Emil Jerabek, who is the world's greatest genius in producing omitting axioms, right? So there are some axioms you would expect that are not here, but Emil shows then that you can prove them from these axioms. So that's PA minus, so an extremely simple theory. Now, okay, sorry, I hope you still have a little bit of patience. So this is my last ingredient. We need because we need to say something about formula classes and the definition of the axiom set of the theory that we are looking at. And so that's, there's this notion sigma 0, 1, and this is simply says that the formula has the form, there exists x as 0, xy, where in S0 all the quantifiers are bounded. So they are bounded by terms. So the main thing to take away from this is that S0 is a formula that is decidable. And so you say that a decidable formula is witnessed, and so that is enumerable, right? So to find, so take a mathematical theorem of the form for every x ax, and suppose ax is decidable. Now suppose there would be a counterexample that has the form exists x not ax. So can we decide whether there's a counterexample? No. So what you can do is say, well, or not in general at least. So you can say, does it work for 0? Does it work? Is 0 a counterexample? Is 1 a counterexample? Is 2 a counterexample? And if there's a counterexample, you eventually find it. But if there's no, you could search forever, right? So that's the idea of an enumerable set, and so this sigma or 0, 1 formulas are typically the formulas that represent such enumerable effects. And so the pi 0, 1 formulas are the obverse thing, namely instead of existential quantifiers you have a block of universal quantifiers. For example, Fermat's theorem for every x, blah, blah, is a typical example of a pi 0, 1 formula. Okay. Okay, now we are almost there. So Goedel invented this whole idea of coding, right? So we can talk about proofs, we can talk about formal systems, and in fact you can define all these notions with great precision. It's about operations on finite objects, right? So that's the important thing. And so, but finite objects can be always coded by numbers, right? And in fact, when Goedel invented this, it was this idea. It was a kind of spectacular finding. But nowadays we are used to computers, and we know that everything can be coded in bit strings, and we know that bit strings could be viewed as binary numerals, so standing for notations for numbers. So it's very easy to see that this whole idea of coding is in fact by now immediately understandable for almost everybody. And so what we can code is the notion of proof, and what we can code is the notion of provability. And so so what we do is we code the notion of proof, and we say, let's see. So A is provable really is, there is a P, a number representing a proof, and such that P represents, P is really a proof of the sentence coded as in the numbers as A, right? So forget about the numeral of the Gödel number, this is all details. So, but really what we can represent is that in arithmetic is the notion that there is a proof of A. And so I don't find this pleasant to read, and so I use this kind of notation with the box. So this means A is provable, and the alpha here is, gives us the axiom set. And so what you can also write instead of the box, the diamond, so that means not box not. And so this means that the theorem axiomatized by alpha plus A is consistent, right? So the diamond is consistency, the box is provability. Okay, now finally we have everything. And so now here you have my formulation of the second incompleteness theorem. So suppose we have a sigma 0, 1 formula, so a formula that enumerates the axiom set of a given consistent theory U. And so, and then the statement of the theory is that U does not interpret B plus the consistency statement for the theory, right? So that's it. So given any theory that is enumerable and where the axiom set is represented by a formula sigma, then the basic theory B plus the consistency statement for the theory cannot be translated into the theory, right? And so you note that the role of the interpretations here. So the role of the interpretation is here. So this is in the arithmetical, it's a specific arithmetical language. So this is a kind of, not in many respects, not coordinate-free formulation. So U can have a completely different language, right? It could be set theory. So because we know, for example, that we can code arithmetic in set theory. But so this statement works very well for set theory too, because it's modulo, we are thinking here, modulo intertranslatability of theories, right? So in some sense, so the precise specification of a language is called the signature in logic and in computer science. And so what we want is freedom from the tyranny of the signature, you could say. Now there's an important remark. There is a different formulation of Gödel's theorem that was discovered by Pfefferman. And that says that if U interprets the basic theory via some translation interpretation K, then U interprets U plus the inconsistency of U. And so, okay, so what this says is really, maybe you can think best in terms of models, right? Consider any model of our theory U. Then inside of that model, you can always, in a uniform way, build an internal model that in which the inconsistency statement is true. So if we confuse interpretability with imaginability, so you could say that every formal theory can imagine that it's a kind. Formal theories are modest. They always can imagine that they're inconsistent. And so they can do something positive, right? They have a positive property, namely modesty. But of course, if you're modest, because everything in arithmetic is arranged according to iron laws, if they can imagine that they're inconsistent, they cannot prove their own consistency. And so, because the point is very often the incompleteness theorems are named as limitative results, right? So that they're supposed to be a kind of weakness of the series. They cannot do something, but that's in some sense not the right way of looking at it. So there is a famous philosopher, John Perry, who collaborated for some time with a regrettably deceased famous logician, John Barwise, and during a talk I heard John Perry say, John Barwise is really a great guy, but he has one severe limitation. He's not able to distinguish things that are easy and things that are difficult. And so I would want to say that the sense in which the incompleteness theorems and the second incompleteness theorem give you a limitation of a theory as a kind of John Perry kind of limitation, right? So the kind of limitation that John Barwise had. Okay, so for the eager mathematicians here in the room, it's a kind of nice homework exercise to try to prove the second incompleteness theorem from Barwise's version. That's okay. Now there is I want to explain to you some further thing, and that's intentionality. So we are thinking about provability, consistency, not in the case of the second incompleteness theorem, not outside in the real world where we all live, but inside the theory. And so certain things of which we know that they are the same are unknown to the theory to be the same. And so the formulation of the second incompleteness theorem is really quite sensitive, in some respects sensitive to details. And so Pfefferman found a very famous example that shows that the second incompleteness theorem is sensitive to the choice of your representation of axiom set. And now I claimed the theorem, and let's go back for a moment. I claimed the theorem, so if the thing is a sigma 1 formula, then we are okay. But Pfefferman found that if you take it to pi 1 formula, so Pfefferman constructs, here it is. So Pfefferman constructs a predicate alpha star such that alpha star represents the axioms of piano arithmetic. So we'll see, okay, piano arithmetic, okay, I can explain easily what it is. It's PA minus, but then plus all the induction axioms, right? If A0 and for every x, AX implies A of the successor of x, then for every x, AX. So extend PA minus with the induction axioms and you have this much stronger theory, piano arithmetic. Now, so what Pfefferman shows is that you can find this alternative thing that represents the axioms of PA. Now suppose that alpha is our usual kind of the canonical representation of the axioms. And then we find something interesting. So Peano believes that for every sentence A is an axiom according to alpha asterisk. Oh, sorry, I took a start. It's an axiom according to alpha star if and only if it's an axiom according to alpha, right? So you have your usual description of the axioms, where in fact roughly the translation into the language of arithmetic of what I just said, right? Take the axioms of Peano minus and add induction. And so Peano really believes of all the sentences that alpha star and alpha really define the same thing. But still, we have that Peano proves the consistency of itself, but then for that other representation of its axioms, right? So that phenomenon is called intentionality, right? And so it means that if you talk about the theory, you really should get into the hide or the skin of the theory and not import the things you know externally. So because for the theory, it's still the differences between this axiom. So even if we know that the alpha star and alpha are the same, Peano doesn't know it, and hence it treats the two things quite differently, right? So that's the phenomenon of intentionality. And so note that, of course, it follows that Peano does not prove for every x a star x if and only if alpha star x if and only if alpha x. So the point is, so for every a in the real world, the theory knows that they're the same, but the theory does not know that they're the same for everything, right? Because the theory doesn't really know that the only numbers are the numbers in the real world, so to speak. Okay, so this is the phenomenon of intentionality. Okay, now we get at this kind of embarrassing problem with the formulation of the theorem as I have given it now, because so these consistency statements are constructed. So the idea is, of course, we have our informal definition of provability, proof system, the syntax, what is a sentence, etc. So you inspect these informal definitions, and then you translate all of it into arithmetic. And now the problem is that this process contains a tremendous number of design choices. You can do many different things, right? So we could, for example, treat conjunction with infix notation. So write it between the conjunction of A and B is A conjunction B. But we could also do it using Polish notation and write it in front of it, right? So we could treat the syntax in different ways. Also, we could treat the syntax as an algebra that is realized in the free monoid. So you build your syntax from strings, but you can also build your syntax from trees. So you can, in fact, choose any data type you want and build your syntax from that data type. Okay, so you can also choose different proof systems, right? You can choose a Hilbert system, natural deduction system. You can, but also you could, again, represent these proofs, even given that you have a proof system, you could represent it in a different way. Okay, so that's the stage. In stage one, you have a great number of choices. And, but in stage two, because now we are going to translate the syntactical objects to numbers. And again, of course, so how can you do that? Well, in any old way you want, right? We can think of many ways of assigning numbers to our syntactical objects. And so what to do about it? And so, Pfefferman is one of the great people of the previous generations, and he wrote this great paper, Arithmetization of Metamathematics, and he had a kind of firm solution. And what was his solution? He said, why worry about this? Let's just here I'm giving you a whole set of choices. So he built up his arithmetization in great detail, and he said, why not simply fix this once and for all? But I think the problem with Pfefferman's solution is that, well, I for one have read his paper, I think 5-6 times, but still I, for the life of me, cannot remember what his Gödel numbering was, how his Hilbert system, he had a Hilbert system, how his proof system precisely worked, etc. Right? So, and even if I could remember it, it's still not the way you understand it, right? You understand it, so in a sense, like take a decent formal proof system, take a decent syntax, take a reasonable, but this quantification of take a reasonable, take a decent is not quantification over mathematical objects, right? So decent and reasonable are not mathematically defined terms, and so the real problem is really, can we get closer to this, to solving this? And so, so one strategy of solving the problem is simply mathematical abstraction, right? So what you say is, okay, so why don't we just zoom in on what is relevant of our proof predicate and simply define provability as something that has the relevant properties? And so what you then do is sit down and analyze. So analyze Gödel's proof of the second incompleteness theorem, and then you get a number of, in fact, 3 important properties, namely the so-called loop conditions. So the first says that if our theory proves phi, then the theory proves that phi is provable. If the theory proves that if provable phi and provable phi implies psi, then provable psi, and if provable phi, then provable phi, right? So the third one is the most interesting one. It's the reflection axiom, right? So if you think about provability as a kind of knowledge or belief, you could say if I believe something, then ipso facto I believe that I believe it, right? Or if I know something, then ipso facto I know that I know it, right? So that's the third principle, which is in some sense the most interesting one. And so the remarkable thing is that these 3 principles are principles well known from a branch of study called modal logic. And so they're the modal system case K4. And so the interesting thing is that we can study the loop conditions using modal methods, and we can link them to arithmetical theory and Gödel's theorem, right? So the loop conditions leads to provability logic, and that's a subject both Dick and Lev and I myself studied intensely. And so the one proposal to get rid of the coordinates would say, we are not worrying about all these details. Anything that has these very good properties, desirable properties, we call a provability predicate, and hence we can also use that to define provability. Now there's still a problem here, because you still need you're rid of a lot of details if you do this, but there's still these, the phi here inside, and the phi arrow psi and the psi inside the box, And these are still coded using Gödel numbers, right? So we are rid of the choice of the proof system and a lot of other things, but you're not rid of the choice of the Gödel numbering. So now, yeah, so there's a lot of research about these things. So Balthasar Grabmaier is precisely trying to get rid of the need to make these choices, and so he's exploring general conditions on possible Gödel numberings and having morphisms between these things, etc. Right? So there are attempts to get rid of this. Also, there are a number of false positives, right? Okay, sorry, I just precisely did this wrongly. I should have written 0 equals 1 here. So forget this one. So 0 equals 1 satisfies, in fact, the oh, no, sorry. No, it is okay. My apologies. No, this one is the right one. So if you look here, so if phi is provable, then 0 is provable. If 0 is provable, and so if you have 0 is 0 and 0 is 0, then 0 is 0. And if you have 0 is 0, then 0 is 0. So if you read for box phi 0, 0, you satisfy all the axioms. But of course, that ain't what I call a provability predicate, right? And so, also, of course, there are also some false negatives. So even in our current formulation, there are certain of the box alpha that are really legitimate proof predicates for which we do have the second incompleteness theorem, but that do not satisfy the loop conditions. And now I think what one should do if one to defend this strategy for coordinate freedom is to claim that at least the false positives are no problem, right? The only thing we need for the formulation of the theorem is if you have these properties, then you have second incompleteness, step 1. Now that's for a lot of predicates. Now, if you give me a specific proof predicate of your choice, then it should be easy to verify that it has these properties, right? So it's sufficient for the statement that you prove it for a larger class of things, because ipso facto it will be a stronger theorem. Yeah, it will be a stronger theorem. And so the whole problem is only that the set of decent things is not a mathematical notion. But so you could try to live with that. So the false negatives, I guess, are more of a problem. Okay, there's here a second solution. Okay, let's see how much time I have. Okay, yeah. I have lots of time, so I can say a little bit more about the second solution too. Okay. Okay, so what we did in the first example, in the first strategy, was simply saying, okay, let's analyze the proof, extract the essence of that proof of Gödel, and then define a kind of abstract system for which the argument still works, and so that abstract system gives us the right properties. Well, another way of thinking about it is to not look at the proof, but looking at what you can do with your consistency statements, right? So what are the powers? So Aristotle would say that the essence of something is given by its powers. And so what are the powers of a consistency statement? Given that you know a consistency statement, what can you do with it, right? And so couldn't we simply try to define what a consistency statement is using its using what it can do, its powers? And so, okay, but then the next question is, okay, but then what are the powers of the consistency statement? maybe I don't know an exhaustive answer, but there is an extremely important power, and that's namely not Gödel's incompleteness theorem, but Gödel's completeness theorem. If I know that the series is consistent, thus speaketh the completeness theorem, then the series has a model, right? So every consistent series has a model. That's Gödel's famous completeness theorem. And now this great theorem throws a shadow in the theory world. And so this shadow is simply that we can translate the completeness theorem in an interpretability power, right? Namely, that if we have our basic theory plus the consistency statement for a given theory U, then we can interpret U, right? So so we can build so in B plus the consistency statement for U, we can build an internal model or an interpretation of U, right? So that's the syntacticized version of the second incompleteness theorem. And so you could try to say, let's give it a name, that a sentence. Okay, we have, there's a lot written. Okay, here. Okay. So you could simply say that a sentence that has this power so if you have a finite sentence that has this power, that it's a pro-consistency statement, and you could try to prove the second incompleteness theorem for pro-consistency statements, right? And so then, because the definition of this power, namely to be a finite theory that interprets the possibly non-finite theory, is a power. Now, of course, if U is finitely axiomatizable, we get something trivial, so that this doesn't quite work. But when you inspect the proof there, it turns out that the interpretation that you get has a number of special properties. So you could improve this by saying that A interprets U and has some special properties. And if you do that, I'm not going to describe this because otherwise we get into far too technical water. But if you do that, right? So if something is a pro-consistency statement, if it interprets U with an interpretation of a good sort, then you can indeed, for this class, prove the second incompleteness theorem again. But of course, now again, this overgenerates, but yeah, as we discussed earlier, the overgeneration maybe could not be viewed as a problem, so we simply prove the second incompleteness theorem for a wide class and say, well, our intended class, the consistency statements, is a part of it. Okay, so now I was, you know, this argument about overgeneration is, okay, it brings you somewhere, but I never felt completely happy with it. And so you can improve this idea to pinpointing really the consistency statements modulo certain equivalence relations. And so you could, so you can define, in fact, the upshot is that you can define the consistency statements modulo a given equivalence relation using in fact the ideas that I described here, but then further refined. But the disadvantage of all those approaches is that still the equivalence relations are too coarse, and so the holy grail of the the coordinate freezing is still escaping us, is the message. But indeed, several people in the world are working on this, and there is some progress. It's clear that you cannot, that there are mathematical ways to get to it that will hopefully bring us a little bit further. Okay, so the last thing I promised, because of course in a very important, okay, the Gödel's second incompleteness theorem was, when proved by Gödel, of course, a kind of big cultural thing, right? It refuted a foundational program due to Hilbert. It had, I think, it's not really needed to argue for its importance, right? It has had this great historical importance, and it still has this kind of great historical importance. But okay, that's true, but is it still productive? Can we still get applications from it? And of course, this is not like the great theorems in analysis where people are producing applications of it every day, right? It's not that kind of theorem, but still it is productive. And so I note at least a few important things here. So remember that piano arithmetic is this weak theory, PA minus, but then extended by full induction. And induction is a scheme, right? It's an infinite. So we write, let's not do that. We write A0, and for every x, AX implies ASX, implies for every x, AX, but the A is an infinity of specific arithmetical formulas that you plug in for the letter A. So piano arithmetic is in fact infinitely axiomatized. And now you could ask, well, is this really needed, right? It's inconvenient if the theory is infinitely axiomatized. Could we replace the infinitely many axioms by a finite one? And the answer is no, and you can prove that. And the most familiar proof for most people precisely uses the second incompleteness theorem. However, there are different proofs that do not use the second incompleteness theorem, right? You can do this in several ways, but using the second incompleteness theorem, you can prove even more, namely that piano, I call that quasi-finite. Piano is not mutually interpretable with a finitely axiomatized theory. So it's not just that you cannot find a finite sub-theory that implies the whole theory, but there's no finite theory that you can translate piano back and forth with. And of that theorem, I don't know any other proof than using the second incompleteness theorem. Okay, so now the theorem plays an extremely important role. Well, I should really say the theorem and its brothers, because during this conference we heard a lot of things about comparison of strings, but it was then hierarchies of reflection principles, but that's in some sense quite related. So, but for example, there's a kind of, so the ordinary set theory, for example, right? So we can interpret set theory in arithmetic. How do you do that? Well, you identify the numbers with the von Neumann ordinals, right? So 0 is the empty set, 1 is the singleton of the empty set, 2 is the empty set and singleton of the empty set, etc., right? So that's the von Neumann ordinals, and they mimic in set theory the natural numbers. So ZF does interpret PA, and so you could ask, so in some intuitive way, ZF is certainly stronger than PA, but is it essentially stronger? And so using this, you can sit down and work and show that ZF proves the consistency of PA, and that shows that it's essentially stronger, because if PA would interpret ZF, it would also interpret its own consistency, and that is impossible by the Goedel theorem. So there's all kinds of speed-up results thanks to a method developed by Pavel Putlak can be proved, right? So there are many series that on a restricted language prove the same theorems, and so you would say on that restricted language the series are the same, but then it turns out that a proof in this, what is in some sense the stronger theory, can be much faster. You can find much shorter proofs in the stronger theory than in the weaker theory. So even if on the restricted fragment you cannot prove more, you can prove things much more efficiently. And so in fact it's super exponential speedups that are relevant here. So these are speedups that stagger the imagination, right? So even 2 to the 2 to the x is a function that grows so fast that it's hardly imaginable. But this is super exponentiation that goes, so that's growing towers of exponents, so that's very quick. So, okay, so degree structures. So the second incompleteness theorem tells us that given any theory, that you have a theory that interprets it, but that's strictly above it, right? So there's no co-atoms, there are no maximal elements below the inconsistent theory in the degree structure of the degrees of interpretability. Okay, a last one. So, well, maybe I should not try to explain this, but the idea is that so you want to given that you have a theory, then you want to know. So you have some extension, and you want to know. Well, the extension seems prima facie stronger, but is it really stronger? And so the second incompleteness theorem helps you in some cases to see that in fact the extension is not stronger, and so you can really interpret the extension in a clever way in the one. And so I discovered that the second incompleteness theorem can help you with that. Okay, so this is the end. Oh no, maybe say the last word. So, okay, so what did I do, right? So I introduced the different ingredients to you, right? So there's quite a lot of ingredients, regrettably. That's why I had to run through this boring list. So so the ingredients were theories, interpretations, and we needed this basic theory B. So that's a kind of new animal in the discussion, I think. And the specific formula classes in which we want to specify our axioms. And I illustrated that if you don't keep to these formula classes, the thing goes wrong, right? So I showed you the Pfefferman example that shows that you lose the second incompleteness theorem if you take different formula axioms from a different formula class. Okay, and then there's of course arithmetization. Okay, then I gave you the statement, and I argued for the kind of point of view that it's not really a weakness but a strength, the property of incompleteness. And then I discussed the business of the coordinates, where of course until now we have to say, well, we are not there yet, but hopefully we get us. In the end, we will maybe find a kind of very good coordinate-free formulation of the thing. So thank you, and here's again a picture of Lev.
Thank you very much for the brilliant talk. Are there some questions? Comments? Everybody understood now what means incompleteness theorem.
Let's take a poll who now knows what it is.
Let me ask you a question. So if a theory includes arithmetics, then it's incomplete.
Then it?
Then it's incomplete.
Yeah, but it
no,
doesn't...
No, let me continue, please.
So
what do you think about the following question? Let us take a part of arithmetic. I don't know in which sense, that we want to get a complete theory, and consistent.
Yeah.
Is it possible?
Well, the problem is that it has to be very weak, because there is even, so for the first incompleteness theorem, you even the extremely weak theory R makes as a sub-theory, makes the theory incomplete. And so it's very difficult. You have to go to a very, of course, so to simply take the language of as your arithmetical theory, simply predicate logic in the language of arithmetic, right? So then, of course, it's still not complete, but it could have a complete extension. So yeah, so because this in my talk, the theory B is very weak, and so the best answer is probably, well, no, if it has even a little bit of arithmetic, namely
yes,
this extremely weak theory of the discretely ordered semi-rings, then you're already dead, right? So the theory cannot be decidable. The theory cannot be complete.
Okay, thank you. More questions, please?
One question. What sort of coexistence between classical, what sort of coexistence is there between classical and intuitionistic logic in the light of the second Gödel's theorem?
Yeah, that's a very good question. So so if we go to the constructive context, interestingly, everything so what works splendidly is my formulation of the second incompleteness theorem, because the proof of that is fully constructive, right? So the incompleteness theorems are fully constructive theorems, and they also work for constructive theories like Heiting arithmetic, which is the constructive brother of piano arithmetic. So the nice thing is, so everything works, but Pfefferman's theorem, regrettably, goes overboard. So you can, in fact, prove that Pfefferman's theorem doesn't work. And so one problem that I have is, so there should be, of course, some kind of equivalent of the insight behind Pfefferman's theory also for the constructive case, but so what is it? But as it stands, Pfefferman's theorem, so the modest formulation goes overboard. Is this the answer? Does it address your question?
I was looking for some general answer, maybe also this philosophical.
Yeah, but so okay, I didn't address the philosophy of the whole thing at all, right? Because okay, I think you really have to distinguish carefully between internal mathematical philosophy, right? So I think in that sense, the coordinate problem, I think that's part of the mathematical approach, but of course there's also the approach, what does it mean for our human powers of cognition, the incompleteness theorems, and do they prove, for example, that we are not machines? And so there's all that discussion. I didn't address this at all because, not because I couldn't, but that would be a second talk. That's also a kind of big subject, and a lot has been written about it.
Well, more questions? Comments? Maybe.
Yes, so maybe that's related to the last remark. So, of course, when we formulate incompleteness, second incompleteness, as a statement that, okay, consistency of a theory cannot be proved in that theory, or consistency assertion cannot be proved in this. The main problem that people here in the audience should be aware of is that this formulation has the following problematic ingredient, that we're saying that a particular formal statement in the formal language of a theory means something.
Yes.
So when we say that a particular formula expresses consistency of some formal theory, we are now talking not mathematics, but rather philosophy.
Yeah.
And this is a main, so to say, philosophical, if you like, problem with this. So it's rather the interpretation of a strict mathematical result that is appealing to us via Goedel, but not the result itself. So the result itself is about non-probability of a particular long, very long arithmetical formula, which is in itself interesting and may have some technical consequences listed on slide, on the last slide, but nevertheless, this philosophical appeal is really of a, let's say, philosophical interpretation of Gödel's theorem, but not mathematical state.
Oh yeah, so, oh no, I don't need this. Yeah, so indeed, so this is what I also classify under the philosophical side. And so I have to admit that for a long, long time, I have thought that all this talk about that the con thing really means consistency was, well, that it was just heuristic or whatever, but I went over to the other side, right? I do think that you can make a kind of story that says that, okay, of course, the arithmetized consistency statement is strictly speaking a statement about numbers. So it speaks about numbers and not about proofs and whatever. But I think you can tell a story that says, well, but of course, you have a sort of kind of embedding of our true talk about strings and formulas, etc., in arithmetic, right? It's a kind of embedding in a definitional extension, you could say. And so I do think that there's a story to be told that in some sense the consistency statements are really consistency statements. But there's a whole discussion of people who have different things, right? So some people think it's really the loop conditions that give meaning to the provability statements. That's one thing that, for example, that I do not tend to believe. And so, yeah. So, but maybe, because I thought that maybe about this earlier question, so I think that the kind of philosophical interpretation, at least for mathematics, of what Gödel did as against Hilbert's program is in some sense simply that mathematics is open-ended. And I think if you look at the two great foundational programs of our day, namely ZF-Z theory, so I think this kind of open-ended view fits it very well, because we don't know what the largest cardinal is, and it's a kind of open-ended thing. And the other one is Martin Luft type theory for the constructive, on the constructive side, and there you think as the notion of mathematical proof as open-ended, right? So in a formal system, the things that the formal system produces are really forms of proofs, not the proofs themselves, right? But these forms of proofs are precisely fixed, so they're in some sense a closed totality, where in Martin Luft type theory, so the intuitionistic foundational program, the proof, what is a mathematical proof itself is an open-ended thing, right? So we can always, the intuition would be, we can always discover new things that are proofs. And it's a new insight that this and this is a proof. It's not already fixed by some kind of preconceived description of what your proofs are. Okay, now I'll try to say a little bit about the philosophical
There is a popular opinion that in some sense the content of Gödel theorem can be reduced to the following expression. This statement is false.
No,
What do you think about this, Naif?
No, okay, so yeah, you should look at it this way. So compare it with fire, right? So the event, fire was a destructive force, and that destroyed everything. But at some point, humanity succeeded in taming fire, right? This destructive force was placed in very restricted circumstances, the motor of an automobile or whatever, and it was made to work for us, right? So the liar paradox, so what I'm now saying is false, is a semantical paradox. So it's about semantics, it's about meaning. And there I think it's a kind of destructive force, and nobody really is able to understand precisely how to think about this paradox, right? But it's semantics, it's about meaning, it's about saying something. So now what Gödel did in some sense was take this destructive force and bring it in a sterile environment. And this sterile environment is namely syntax. Right, so he is not, so formal provability, that's what we are speaking about here, is not intuitive provability. That's precisely the point about the open-endedness of intuitive interpretability. No, it's a kind of very precisely specified notion of provability. And now it turns out that what was this paradox that we didn't know how to handle, now in this sterile, good environment, safe environment, it's starting to work for you. And so the Gödel sentence in fact is something like, I am not provable, but it's not provable in this intuitive sense, it's provable in this very safe sense. And so what was a paradox in semantics becomes a theorem in the formalization of series, right? So that's the kind of way I look at it, right? So it is, you're right, so it's very much related to the liar paradox, but it's the liar paradox tamed in a kind of extremely safe environment where we are the boss.
Thank you. One last question, if there is.
In your opinion, what is it mathematical totally? Do you think about it? And if mathematics consists of противоречивых ветвей, is it possible to understand each other, and is it possible to translate results from one branch to other and vice versa?
As I understand the question, it looks like the following. If there are contradictions in mathematics, how we can understand each other?
Oh, okay, yeah, so...
Is it okay?
Yeah, if that's the question, let's try to... So, okay, I, of course, have no absolute authority on this question. But, I think that, yes, mathematicians can understand each other, and also in different branches, right? So, I'm not a formalist, so I believe that our mathematical language has content. So if we state a theorem, we are saying something, and it's And this content is, so our language and the way it expresses the content is a shared language, and so the mathematics is of the nature of the thing that is shared. Yeah? In some sense, I think it's not so much in that it's not so much difference from our shared reality here, right? So we all see this computer, and you all see the same bottle of water that I'm holding here, and I think that it's like that, and so that learning, of course, if you would come to our conference, and if I would come to your conference, of course, we wouldn't understand a word at first. But yeah, so I don't think this is a matter of principle. So there is, of course, the matter of the finiteness of our lives and the limitations of our intelligence. But okay, that could make mutual understanding between different branches difficult. But I think that's not okay. That's a matter of, well, very big practice, very big practice. But it's not a matter of principle. So I would think that mathematics is a kind of something that is there for all people.
Okay, at least positive note. Let us finish the seminar. Thank you very much again.